Hey, good morning, everyone. Good morning.
Good morning, Professor.
Good morning, Professor.
Hi,
Good
good
morning.
morning, Sarah. Good
Good
morning,
morning.
Anna. Good morning, Jalen. Hi. I didn't see anybody in today's forum. What's going on? Were you not able to find today's forum? Hmm? You see,
I I posted and I saw like a couple other people, like six other
you
people.
did?
Yeah.
This is your class.
It says
Oh,
24. It's the
oh,
22nd. That's
22.
why.
Yeah, I'm sorry.
It's okay.
All righty. So you guys are there. You guys are there. All right. Um, so I see 7 here, and I see also 7 here. Um, you guys are all on time, and hopefully the rest of the class will soon catch up. Um, of course, they will. The rest of the class will join. Shortly, hopefully. All right. So today we are now moving on to the new topic. Um, this is, yeah. We are into time value of money, right? The third topic. And actually, time value of money, we've actually uh, dabbled with this in topic one, actually, because it's closely related with the house value example we did in topic one. And once you check into this folder, then you need to download these two files, especially the Excel file. Excuse me. And all these, these gray, they are grayed out because, they are already passed. So you must be, what is active, current and active as of now are these. So you will need to be, and then still, these other videos will still become active on March 30th. So, excuse me, you need to be caught up all the way to these videos, and the past ones, of course, they are, excuse me, allergies season, you need to find them on the, you should have already watched those videos. But if you need a refresher, you can find them on my YouTube channel. Okay. All right. So let's see. So what we are going to look into in topic 3 is time value of money, and of course, time value of money uh, is the basis of finance. I mean, it's the foundations of uh, financial math. And in finance, basically, the relationship between the future value and the principal is very important. And this is something you already know. Future value is price times, I mean, not price, principal times 1 plus r raised to n. Okay? This is nothing new. You've seen this before. Where? In topic 1. Remember, in topic 1, we talked about, compounding, and this process is called compounding, right? Principal, uh, the principal will earn interest, right? Or for n years, right? Or n number of years or n periods, the principal will reach certain future value. And you've seen this in topic 1 because we were talking about house values. And in house value, house value is inevitably uh, related to the time series. Remember, the data can be cross-sectional or time series. Time series is also called historical data. Um, and uh, whereas, it's also called longitudinal data, remember, time series, historical data, or longitudinal data, they all mean the same thing. And whereas, cross-sectional data means, latitudinal data, and it is, basically, it has nothing to do with the time dimension. Um, it's literally, synchronic. Whereas, or static, synchronic or static, right? We're not observing anything. We're not observing a data series that's reflecting the change over time, but in a cross-sectional data, it's just static, right? You're looking at data over a static time plane, so that's why it's called latitudinal or synchronic as well. But in the house value example, of course, the house value grew. Remember, I mean, from time 0, time 1, time 2, time 3, and and the house value grew, right? Starting from 50K, and over time, right? It grew, right? So this doesn't help. Okay, it takes time for the dots. So you at the time you've seen that there is a compounding effect going on. Compounding effect. Why? Because it's because the house prices are correlated with each other. I mean, second year's house value is the result of the growth from the first year's house value. Third year house value is the result of the growth from the second year, and so on, right? So you understand quite well from that. In topic 1, we already talked about what compounding is and how it is mathematically how it is expressed, and also I said when we talked about the classification of the interest rate, I also talked about compounding, compound interest rate, and difference between compound interest rate and simple interest rate, right? And I said, compound interest rate is better. compound interest rate is used in the capital market, right? Whereas simple interest rate is used in money market, right? Do you remember? And the money market is a short-term financial market. Capital market is a long-term financial market, right? And of course, the line between short-term and long-term is 1 year, right? So if the maturity is less than 1 year, that's money market, right? If the maturity or the timeline is longer than 1 year, that's long capital market. Now, so with that in mind, we already know how the compounding works. Future value is basically a principal times 1 plus r raised to the nth power, where n being the number of compounding periods, right? Or interest rate. Now, one thing we need to understand is that of course future value is the unknown here. Future value is the unknown, right? Future value is the unknown. Question mark. But the others are all known quantity, right? Principal is the known quantity. Interest rate is also the known quantity. N is also a known quantity. I mean, something like if you put if you put 10K, let's say, in the bank for 5 years, where interest rate is 10%, then we know, right? All of these, are known quantity. Principal, interest rate, N, they are all known quantity. So future value is the unknown quantity. So we are solving for future value in the very basic compounding model, right? Whereas, however, think about it. This is just one question or one equation that can arise from the compounding formula. In other words, if you want to know what's going to be the future value, in other words, when other variables are given, when other variables are known, all we need to do is just solve this by using this formula. And if you do that, we can easily, by plugging it into a calculator, you can easily find it.
I have a question.
Yes.
What if the interest rate, what if it's a variable interest rate? Would that change the formula, or?
We will have to assume, we'll have to assume fixed interest rate. But, if the variable rate, if the rate is known, for example, between, let's say, between year, time 0 and time 3, let's say it's 10%. And then between time 4 and time year 4 and year 7, let's say, year 4 and year 7, interest rate is 8%.
So
if this is known, we can do that. Because, for the first 3 years, we can apply, 10% interest rate and raise it to, for example, it's going to be then right? It's not a difficult thing. But the point is the rate needs to be known. I mean, if this is the case, right? Think about it. The future value will be then, if that's the case, then the future value will be 10K times 1.1 for the first 3 years, right? And then after that, so this result will be then, will grow.
Also, the future value will
1 point,
become the principal for the next one.
what?
Well, so the future value will become the principal for the next.
Yeah, of course.
Oh, okay,
After year
okay.
three, this will be the principal, right?
That
But
makes
of
sense.
course,
Okay.
that's as of the end of year 3 or the beginning of year 4, right? And then it's going to be, raised to how many years will it be? 4, 5, 6, 7, right? For 4 years, right? It's going to be, right? So this way, that's going to be the future value, right? At the end of year 7.
Okay, that makes sense. Thank you.
Right. You're welcome. Now, so our next question is, as I said, okay. So we can solve for this using a calculator, which is not a difficult thing. All you need to do is, I will just but it will have to be a scientific calculator because you're going to need to raise it to power. 10K times 1.1 raised to 5. All right, it's going to be 16105.1, right? And it's going to be 16,105.10, 10 cents, right? Okay. Finding future value, we follow the, we just, need to follow the formula. But, the second, think about it, there can be a second question. What would be the second question? The second question will be, what if principal is the unknown? That's all possible, right? Think about it. What if this is known? In other words, 5 years later, you want to have 16,105. Currently, the interest rate is 10%, right?
So
Then what should be the principal, right? What should be the principal? This can be the unknown, right?
so you would have to rewrite the formula to have P on the equals side instead of FV.
Right. In other words, you will need to solve this equation for P, right? And of course, we know because we have already solved it for future value, and then we know the answer. It would have to be, $10,000, right? But it's not a difficult thing to solve for P because um, we know basically when we have, think about it, when, oh no, what am I trying to do? All equations, no matter how complex they may look, all equations, basically all equations, if you can identify this z equals x times y structure, all equations can be solved. It's only a matter of
Yo,
identifying
Gachi,
this structure.
can you buy sandwiches?
Okay, you will need to mute your microphone if you are.
Oh, I'm
No.
sorry. I'm sorry.
Alrighty, so think about it. All equations, as long as you can identify this structure, right? It's only a matter of identifying this structure, because basically it's like we all know 12 equals 3 times 4, and we know uh, what if this is the unknown? What if you don't know this? What do? You just need to divide 12 by 4, and then you'll get 3, right? So it's the same concept, same idea. What if x is the unknown, right? Then solving for x, you need to divide z by y. Ah, this is z by y, right? So as I said, that is only a matter of identifying that structure, right? That pattern. And do we see that pattern here? Yes, of course. We see that pattern. Think about it. In this formula, right? In other words, uh, moves FE equals P times, right? I'll just put it like, the thing in the bracket raised to n, right? 1 plus all raised to n, just to make it, quicker and, easier, uh, so that I won't have to spell it out all the time. And then you can tell, oh, change the color to something like this. So this is like z, right? This is like x. This whole thing is like y. And what do? I mean, x is the unknown. In other words, p is the unknown. Well, what you need to do is simply, then solving for p, you will need to. And p is Fe over so yeah, there we go. Fe over 1 plus r raised to n. Okay, and we can easily find, a present value. And if you do that, exactly we know what we'll get. We're gonna get to 10,000. And if you solve this equation for principal, that principal is also called the present value. Why? Because that's what that 16,000. That's what that future value is worth today at present, right? So in other words, that's what the 16,105 is worth today. right? And we know the answer, so we can, but let's just verify. It has to be, um, it has to be 10K, and just verifying, right? Where is, oh, okay, I'm gonna have to, so now this time we'll divide it by 1.1. We don't need to put the parentheses, but that's fine. 1.1, because it's already, raised to 5. If we, so we divide by that, you got to get back to exactly 10K. Okay, so now we want to do the exercise, right? I want you to, download this file, right? I showed you the Excel file to download, okay, from our contents, topics folder, right? Topic 3. I told you to download these two files. This is PDF. That's less important. This is the Excel file. You need to download this and have it in front of you. Okay, please download it now. All right, do you all have it in front of you? Do you have this file in front of you?
Yes.
Okay, good. And you need to be on the first bottom tab, right? That says single cash flow. If you just open it, you might be here, but you need to be here, okay? Okay, let me take my lozenge to soothe my throat. Alrighty, so first example, that's our example that we just used, 10K, 10K, 10% APR, annual percentage rate, 10%, time. This one is the only thing that's different. We'll just change it to 5. If you change to 5, this also changes because it is linked to, it is made to be equal. It was made to be equal to C2. So, and let's find the future value. And the future value, right, is then, what did I do? A2, the principal times, 1 plus R raised to 5 years, right? Okay, and there you go. You will have exactly 16,105.
Professor, I'm sorry. My file is different. This is
What's different?
it's a different numbers and different formula. So
What do you mean?
I'm
Are
not
you?
sure.
Well, please speak up. I told you to go to single cash flow, the bottom tab. And first of all, your files, when you downloaded the file, are these all blank? The highlighted cells, are they all blank?
Yes, Professor, I found it. Thank you.
Mm-hmm. I told you, bottom tab, you gotta look for single cash flow bottom, the first bottom tab.
I also have a question.
Yeah,
What does M stand for?
I'm gonna get to that.
Oh, okay,
All
sorry.
right. So for now, did you all get this result? The same result?
Yes.
Okay, good. Now, next. So what is M then? M is actually, compounding frequency per year. In other words, compounding doesn't have to be just once a year, right? Compounding doesn't have to be only once a year. Okay. Compounding can happen twice a year, meaning, every 6 months. A semi-annual compounding, right? So M can be 1, 2, 4, 12, 52, or 365, or even more. Now think about it. If M is 1, that means, annual compounding. Compounding happens just once a year at the end of the year. If M is 2, semi-annual, every 6 months. If M is 4, that's quarterly compounding, quarterly, right? 12, monthly compounding. 52, weekly compounding. 365, of course, daily compounding. And even it can be by the hour. If it is by the hour, then 365 times 24. It can even be by the minute. And 365 times 24 times 60. It can be even by the second. Then it will be 365 times 60 squared. I mean, it can be by even nanosecond, right? Nanosecond is 1/1000th of a second, but theoretically so. But in reality, only in most cases, for practical reason, daily compounding is most common. I mean, if they push it to the limit, but there's even continuous compounding, but that's mostly for just research purpose and um, theoretical research purpose, um, but also to uh, emulate um, the continuous nature of continuous change, the nature of the continuous uh, change um, in the uh, in the future value forecast, or basically when that's another story. But for now, it will suffice to understand that the compounding frequency is it's like our calendar time cycle, right? Now, so in our example, if compounding is once a year, our interest rate will be just 10% because that was, APR, annual percentage rate. But if the compounding is twice a year, it can no longer be 10%, right? It's understandable because that 10% is APR, right? Annual rate. So if compounding is semi-annual or twice a year, then the rate that actually applies for each compounding, it would have to be adjusted. And it's not difficult to understand that it's going to be 5%, right? It will have to be 5% if it is 2. Come on, what's wrong? Ugh. Well, there's so much delay, like time lag, when I after each of my stroke, it's just, still 5%. And think about it. If the compounding frequency is 4, that means quarterly compounding, then it will have to be 2.5%, right? Because, right, so what do you see from here? What you can see from here is that the
You have to
our R, right, our
divide it by the month.
right, not by the month, but by the compounding frequency,
Yeah, yeah.
right? In
That
other
makes
words,
sense.
R is basically APR, annual rate, divided by M, the compounding frequency, right? So if it is 12, then 10% divided by 12. I mean, you need, it only makes sense. It's only a common sense that the annual rate must be adjusted for its compounding frequency. And so this is called, so R is called periodic rate. Periodic rate, right? Um, Literally meaning, that's the rate that applies each compounding period, right? Every compounding. And then time, it must also be adjusted. Um, think about it. Time has been so far, general time has been uh, expressed in years all this time, right? T, right, has been in years. But if the compounding frequency is 1, of course, it's still the same t, right? In our example, it was 5, right? Time was 5 years, right? But think about it. That's because compounding is annual. If the compounding is semi-annual, how many compoundings actually happen during these 5 years?
Every
Hmm?
6 months,
Every 6
two
months.
times,
So how many compoundings?
2 times.
2 times only? It's 2 times per year, but what is our time?
Oh,
What's
10,
our time
10
length?
times,
Yeah,
10 times
5
for
years, so
five
it's going to
years.
be 10 times, right? 10 times. And if it is quarterly, right? If the compounding is quarterly, right?
20 times.
Yeah, it will have to be 20 times, right? Ah, this is so annoying. I mean, it's not that you think it is intuitive to use the whiteboard. Yes, it is, but you have to always switch between this function and that function to move it around. You have to hold this, pause this, and and then when you come back, it's so. Now, general rule. You also find the general rule here. Uh, and what's the general rule? Uh, we'll call that n. Now, n is. Let me switch to okay, and then so n is the actual number of compounding, and the actual number of compounding is we see that, it's t times m, right? T times m. And this, so t means, just time in general, and usually it's in years, but, now n is the, what?
The total compounding in a year.
Right, total compounding period, not in a year, during the entire holding period.
Yes.
Right? So that's the actual number of compounding, right? Or total number of compounding, right? Ah, oh God. Why is this giving me such a hard time? Actual number of compounding. Okay, actual number of compounding. Okay, so now we are, better equipped than before, and we can handle this second example. Take a look at the second example. In the second example, we can tell it's quarterly compounding. Then what do we do? Before I move on, so that was Samira, right? Samira. That
Yes.
gave those Samira. So you'll get 0.5 for the participation, right? Now, so we know it's going to be, my keyboard isn't, okay. So it's going to be principal times, open parenthesis, and 1 plus APR divided by M, close parenthesis, and raised to. And I've been telling you that symbol is a universal machine language for raising something to power, right? So raised to t times m. Okay, and hit enter. You'll get 16,386, right? 0.16, right? So here, two things. First, the parenthesis here, this parenthesis, right? What I'm talking about is, you can't do that when it is in formula view. Yeah, you can draw. Okay, but then I'll have to. So why is it in the parentheses? It has to be in the parentheses, because if you don't put it in the parentheses, what's going to happen? This will happen first, isn't it right? It's PEMDAS, right? It's PEMDAS, parenthesis, without parenthesis, then what? Exponent, multiplication and division first, right? So you have to put that in the parenthesis, otherwise this will happen first, and that result will be multiplied by this. Then it's going to be a totally different thing. So you got to have, you got to put them in a parenthesis. And the second, although we have the same principal, same APR, same 5 years, future value is greater when the compounding frequency is higher, right? So under the same conditions, even under the same conditions, the higher the compounding frequency, the greater the future value. Okay? Now, row 6, if you go to row 6, you know already It's the same thing as this one, row 3. It's the same thing. But here, I made a slight change because I added, two more columns. I added two more columns, and which is what? Instead of what I did was instead of making that adjustment inside the formula, instead of doing it like this inside the formula, right? Uh, I made that adjustment outside the formula. So in column E, I put the periodic rate, which can be simply this divided by this. There you go. And here n is t times m, t times m. All right. And then future value will be now simpler. Why? It's going to be principal times 1 plus. Now, without having to make adjustment inside the formula, we can just click this in because the adjustment has already been made outside the formula. Right? And then raised to n. Right? The formula gets simpler. There you go. We get to the same result. And the simpler it is, there's a benefit. If the model is simpler, it's going to be easier to detect the source of the error. If ever there's an error, right, in the model, it will be easier to detect the error. The more complex the model, it will be more difficult to detect the error. And if you can easily detect the error, you can easily fix that error, right? So that's the benefit of a simpler model, right? All right. And then once you're done with this, now this is the beauty of Excel. Now think about it. You have 5 more problems to do, right? If you were doing it on a calculator, no matter how advanced calculator you may have, right? You will need to input the data all over again. You need to input the data and do the calculation all over again, one after another. So even with a very highly advanced calculator, it's going to be a tedious job, right? And it's tedious and it's meaningless. I mean, it's not adding any additional meaning. It doesn't add any additional meaning to your learning. It's just repeating the same calculation over and over. So that's why I'm saying it's meaningless, uh, which is rather tedious, right? But then with Excel, all you need to do is, because as long as they are the problems of the same pattern, well, all you need to do is just highlight these 3 cells and simply drag it down, and then the formula gets copied. So all those problems can be answered all at the same time in a single shot without having to solve every problem one after another. Right? Does that make sense? So everyone got the same result?
Yes, but I have a quick question.
Okay, hold on.
Okay.
So if you can you hold that question for a while because it's 11:51, so this is a good time to take a break. So hold that question. We'll take a break first, 10-minute, right? 10-minute break first, and then when we come back, then I'll take your question. Okay?
Okay, that works.
All righty. So let's take a 10-minute. Okay. All right, we're back. We're back. So there was someone who had a question before the break, right? Who was that?
That's me.
Okay, Lewis, go ahead.
So periodic rate is R over T, and
No,
then
no, no,
N is
no. Periodic rate is APR over M.
over N. Oh, okay,
M,
I gotta write
M,
that.
compounding
M.
frequency. M.
Okay, let me write that down. Where's my pen at? So periodic rate is R over M,
Yeah,
and then N is T times M.
yeah.
Yeah. Okay.
N
Cool.
is T times M.
Okay. Thank
Yeah,
you.
you're welcome. Yeah, here in the whiteboard, I wrote it down. I wrote it clearly uh, like this, R, the periodic rate, is equal to APR over M, and N is T times M, right? All righty. So now we can move on to row 14. Now this is exactly our, we did this also by calculator, um, finding the present value, right? In other words, the principal, finding the principal. Now, if the future, it's exactly the same scenario, but we are now, it's the mirror image. We are solving for the principal. Um, so if we know it's going to be exactly 10,000, right? We know the answer already. Let's see if it's, if it can be verified. Yeah, we'll verify it by Excel, right? Uh, so first, future value divided by 1 plus R raised to raised to 5, right? Oh, you know what? This was not in our example. This was future value was this, right? And then was it? It was 10%, right? Not 6%. It should be exactly 10,000, right? And then this one, uh, when the compounding frequency is quarterly, right? uh, the future value is this. And if we work it backwards, so if we work it backwards, you're gonna get exactly the same 10,000 because we started from 10,000 and got to this by quarterly compounding. So you don't need to build it again. You can just drag it down. No, no, no. We need to build it again here because it's not the same. We need to make adjustment here. So basically, future value divided by 1 plus APR divided by M is to T times M. Okay, and then we should get 10,000. Yeah, I got to 10,000. Look, here's the thing. Okay, let's go back to row 3. And here, our formula is exactly like this, right? So what I want to do is I want to drag it up. I want to drag it up. That way, we will have the same uniform formula there. Yeah, now the formula is like this. And of course, nothing has changed. The result doesn't change because D1 is just 1, right? M is 1, so it's not going to make any difference. But then this way, we have a consistent and uniform formula, right? And that's important because when we have consistent uniform formula, then um, we can replicate it. We can replicate it wherever necessary. So here also I want to. Currently it is like this, but I want to copy and drag it up, and then we'll have the same formula, uniform formula, right, consistently, and it doesn't change anything. I mean, but we can. What if the variables were different? For example, this wasn't, remember our original example, it was 50K, right? And then this was 6%. It will automatically, give you what should be the principal. Again, if this is, E14, right? In other words, same as this 50K, it will tell you what should be the principal, right? Now, you see, the principal doesn't have to, the principal is smaller, principal is smaller, or the present value is smaller when compounding frequency is higher. Why? Because remember, the higher the compounding frequency, the greater the future value. But in this case, the future value is the same. So if the future value is the same, then principal doesn't have to be that much. The principal can be smaller, and you can still reach the same future value. Okay, that makes sense? Now, our next, let's move on to our next case. Our next case is, alrighty, so we've been, let's move this around. Now, we've been thinking about what kind of questions can arise, or what kind of questions can be asked from this base formula, right? First, the base formula, which is future value, which is called compounding formula. And if you solve it for P, it's called discounting. So discounting and compounding are reverse processes of each other. They are reverse process of each other, right? So this process is called discounting. The discounting is the reverse process of compounding, right? They are reverse process. Now, think about it. The second question that can arise was, what should be the principal? I mean, when you have a target future value, you have already known future value, so you know your target, right? Target future value. And then, the other things are known, right? Future value is known. Principal is the only unknown, right? Rate is known. Time is known. But the third possible question that can arise from this I put it in the wrong place. It's almost like okay. I'll have to so it's in the middle of, so it will have to get I have to get down to, that was placed in the middle of very awkward place. So the third question, right? Let me repeat. The first, the base formula, compounding formula, right? Future value P times 1 plus R raised to N. Second question, what is P? future value over 1 plus r raised to n. 3, then next question is, what if r is the unknown, right? What if the r is the unknown? But you know this already, actually. You know the answer to this already. Why? But it's a very. So it's we know the future value already. You have a target future value. Something like 16, 105, 10, something like that, right? You have the target. You know the target future. You already have the principal. Principal is 10. So your question is, you're going to put 10K in the bank today, and in 5 years later, right? Or in 5 years, uh, you want to have this. You want to have this future value in 5 years, right? Then what should be the question is then, what should be the interest rate, right? This is the unknown, right? So that's quite a plausible um, likely situation. I mean, what is the interest rate? I want $50,000 in 3 years. I have $30,000 now. If I put it in the bank and I want it to grow to 50K in 3 years, what should be the rate? And right, solving for rate, you already know this. How come? How do you know this already? Ring any bell when I say you know this already? Does it ring any bell?
Because we already have the formula, so we just have to solve for r.
Yeah. But you know the formula already. You learned it already.
Yeah.
Where? From
FV
when
equals
and
P.
where? Huh?
The FV equals P 1 plus r over n.
No. That's the base formula, right? F equals P times that P times 1 plus r raised to n. That's the base formula. But what I'm saying is you know the answer to this. You know the answer to this already because
Oh,
you've
because
seen it
we have
before.
the periodic rate formula, which is r over m.
What? You don't have the periodic rate. That's not it. That's not it.
Oh, I don't know
That is just APR over M. But think about it. I'm talking about how would you find? I mean, this is basically APR, right? When you have your target future value, when you have principal, when you have N, right? How do you find R? Of course, we've been using the same example, so it must be, then 10%, right? But no. In this context, yes, it is, with these numbers, right? With these input variables, with these, initial input, yeah, it will be, 10%. But what is the general formula? What is the formula for R? I mean, how do you find R? Um, I said you already know this. How? Because you've seen this before. When? At the beginning of the semester. At the beginning of the semester. That was when we were doing, topic one. When we were doing topic one, in other words, house value and everything. Doesn't it ring any bell when I say house value, holding period return? I mean, what was the thing that we were most, that we were, engrossed in? What was the thing that we were really, busily engrossed in? Hmm? At the time, our first.
Professor, can you hear me?
Yeah.
Okay. Is it interest equal price RT?
Interest equals what?
PRT, the formula.
No, actually, that's just interest, dollar amount of interest. What you're saying is, um, what is the dollar amount of interest? Of course, that interest is P times R times T, but this is, simple interest. This is the case of simple interest, right? We're not dealing with the simple interest. We are talking about the compound rate, right? Now, remember, in topic one, we were talking about the house value, right? And the reason we were talking about the house value was to understand what is the ROI, how we calculate the ROI. And ROI in the house value, there were two things. First, there is, holding period return, right? And then there were, two scenarios in the house value, right? Scenario one, scenario two. But regardless, I was holding period return. And since holding period return cannot be compared with each other, right? If the holding periods are different, there can be no comparison. I mean, there's no way you can compare return on 5-year holding period, return for the 5-year holding period with return on an investment for 20-year holding period. That cannot be compared. So what did we need? Need to do? We need to find the annualized return, right? And to find the annualized return, what did we have to know? To find the annualized return, what did we need to use?
Future value minus present value divided by present value.
No. I mean, if you do that, that just gives you a holding period return. What you said was, look, if you do
Was it the geometric average?
Yeah, you're right. Who said that? Who
Lewis.
said that? Lewis. Okay. Lewis, you're getting 0.5. Yeah, you had to find the geometric average, right? To find the annualized return, right? You had to calculate the geometric average. Come on. Okay. It's so slow, huh? Remember? Geometric average, right? So in other words, because of compounding, we cannot use simple average or arithmetic average. You need to find geometric average. And basically, what is geometric average? So basically, geometric average is it's the growth rate. It's the return in scenario one. It's the annualized return in scenario one. And the geometric average formula for geometric average was at the time future value over present value, right? Raised to 1 over n minus 1. Okay? But think about it. I told you this was also called, this was a growth rate, but the growth rate is exactly the return in scenario 1. Growth rate and return are different in scenario 2, but in scenario 1, since there is no additional cash flow, right, but just the capital gains, right, growth rate is exactly the return. So in other words, this is also called CAGR, meaning a compounded annual growth rate. It doesn't have to be annual only. Depending on the compounding frequency, it can be even monthly or quarterly or whatever. But if as long as n is years, then that's compounded growth rate. But again, this is R in scenario 1. Now think about it. And at the time, I just gave you this formula and told you to just memorize it because we were not there yet. At the time, we were not there yet to understand how this formula is derived. But now is the time to understand. Now you can understand how this formula is derived. So let's think about it. How it is connected or related to this base, right? This base. Now think about it. So I'm gonna have to. It's moving very slowly. So the base formula is this. And I told you P is the same thing as PV. Principal is the present value, right? 1 plus R raised to N. So this is almost like, and our unknown is this, right? R is the unknown. Right? R is the unknown. To solve for this R, then we need to isolate R. But how do we isolate R? It's difficult. It cannot be isolated immediately. Why? Because it's inside a cage. This is the cage, right? And then it's got a padlock on it, right? It's like a padlock, right? It's like a padlock. So first, you'll need to open the padlock, and then you can open the cage, right? Then you can, but since we cannot immediately isolate, this term R, we will need to isolate first this term, right? This whole thing, right? So how do you isolate it? Well, of course, you'll have to divide both sides by P so that, then it will be isolated. If you divide both sides by P, the left-hand side will become FV over P. And then the right-hand side, P will, cancel out, P over P, right? It's going to be 1 plus R raised to N. Our next question is then, how do we open this padlock? Now,
Radical. radical is a function that is function the raising.
Rating function? What function are
No,
you?
Professor, radical.
Radical, yeah, radical,
Yes.
yeah, of course. You mean square root, the root, right? Radical. So to understand, first of all, let's think about it. So I'll have to bring it in. We all know if we all know that we know 2 squared. It's not, why is it not respond? Yeah. See, almost 5 seconds later. This is crazy. It just appears 5 seconds later. 2 squared, we all know, is 4, right? But then if you take the square root of 4, right? Take the square root of 4. Then it's the same thing as taking the square root of 2 squared. I mean, usually, you might think, square root looks just like that. And what is that 2, that's originally, it has to have 2 here, 2 here. That means that's the square root. Why? Because there isn't only square root, but there's third root, fourth root, any, nth root whatsoever. Why? Because think about it. Um, 2 cubed is 8. Now, when you take the square root, right, it becomes 2, right? When you take the square root of 4 or square root of 2 squared, that becomes 2, of course. In other words, the root of 4 is 2, right? That's why it's called, square root, right? The square root of the root of, that's why also it's called radical, right? Radical. And so just the same, if you take the cubic root, how do you express cubic root then? You put 3 here, right? And the cubic root of 8, it will be 2 in the same way. Also, we all know 2 raised to the 4th power is 16. So if you take the 4th root of, or 4th radical of 16, it's 2. In other words, there's we all know, it's simple, we can extend this to, we can extend it to any number. For example, any power of 2. So let's say 2 raised to nth power, 2 raised to nth power, whatever it may be. Let's call that x, right? If 2 to the nth power is x, then if you take nth radical or nth root of x, that will be 2. Another way of writing that, another way of writing it is, another way of writing it is 4 raised to half, right? Or it's the same thing as 2 squared raised to half. So what do you see? Something raised to half power means square root, right? Something raised to half power, that means squared root. Now, so something raised to so 8 is, we all know, also 8 is, 2 cubed, right? If you raise it to 1/3, right, then it'll become 2, right? Also, 2 squared raised to half power, because it's the square root of 4, right? Square root of 2 squared. By the word, by the word, I mean the language itself already. The square root of 2 squared. Think about it. The square root of 2 squared. The square and square cancel out, so it should be 2, right? From the language, by the language itself already, So if you keep doing this, we come to the some generalized rule that if you raise x to the whatever this number may be, right? But it must be the power, nth power of 2. This x must be the nth power of 2, right? Then raising something to, right, nth power. So this is another way of saying 2 to the nth power raised to 1 over n, right, equals to, it's the nth radical or nth root. Okay, now again, I want to draw your attention. I want to draw your attention to the PDF file. You must study this. It's there. Some rules of exponent, right? There are, first, generally we all know anything raised to 0 is 1, but you just memorize it. You just don't, without understanding why. I'm going to talk about that later. But one of the rules of power, right, is power of power. In other words, there are many rules, but come on, now it is not. One, so I think I might. So one general rule you find is that if you have x raised to a, that thing raised to b is the same, is basically x to the a times b. Okay? Also, when you have x to the a times x to the b, x raised to the b, right? It takes forever. Then it's x to the a plus b. Okay. So if the base is the same, right? The base is both x. I mean, if the base is different, you can't do this. As a simple example, as a very simple example, you have, let's say you have 2 squared times 2 cubed. What is that? It's 4, right? 2 squared is 4. 2 cubed is 8. 4 times 8, 32, right? 32 is what? 2 to the 5th is 32. Isn't that right? Exactly by, adding those numbers. But here also, let's do a very simple example. A very simple example of this. Suppose we have uh, 2 squared raised to the 3rd power. And then 2 squared is, of course, 4. 4 to the 3rd power, right? 4 times 4 times 4 is 64. And 64 is what?
4 to the
2
fifth.
to the
Yeah,
6th.
2 to the fifth. Yeah. Oh.
Right? It's 2 to the 6th. So, the rule, basically, can be verified easily. Now, if that is the case, then if we have, I have to move this again. So in our example, right, we have basically something raised to 1 over n is the radical, right? The root of the number. So that means, if we have x raised to n, then raised to 1 over n, then what do? X to the n times 1 over n, right? One over n. And then think about it. When we have something like, n times 1 over n, what happens? They will have to cancel out. They will have to cancel out. And then it becomes just x, right? That's why, think about it, in all of these examples, that's why it becomes a square root. When you raise, 4 to, when you take the square root of 4, which is, basically 2 squared raised to a half, right? This 2 and 1 over 2, they will cancel out. So it becomes 2. 3 times 1 over 3, 3 and 3 cancels out. That's why it becomes 2. Now, this property is used very, it can be used very useful. It can come in very useful. It can come in very handy. I'm racing with time, so I'm getting tongue-tied because it's already 12:40. But we're about to close. We're there, but this whiteboard is just slow as hell. So here, how do we open this padlock? How do we open this padlock? Well, what you need to do is, basically think about it. You'll need to think about it. If we raise the right-hand side, I'll just put it like, something in the bracket. It is raised to the nth power. So if you take the nth root or nth radical of this, then these two will cancel out and the cage will open up. The padlock will be removed and the cage will open up. But when you do this to the right-hand side of the equation, you have to remember that we are dealing with an equation. That means when you're dealing with an equation, the right-hand side and the left-hand side, the ratio, they must be held. They are held equal. I mean, they are balanced out because the equal sign means, if you do something to one side, you have to do the same thing to the other side as well. So the other side. So the other side, I'll just call it the thing in the bracket. It needs to be raised to 1 over n as well. Okay? So then if once the padlock is removed, then the right-hand side will be simply 1 plus r. And the left-hand side will be fv over p raised to 1 over n. Now, since we are solving for what? We're solving for r. We isolate r. Then what does that mean? This one will be transposed to the other side. In other words, we subtract 1 from both sides. Then we arrive at, what do we have finally? We have r equals right, fv over p raised to 1 over n minus 1. Okay? So we arrive at this formula. Then isn't that exactly geometric average formula, right? If we just replace this with g, right? It's exactly geometric average. This is what you already saw in topic 1. All right. So we're already past 6 minutes past our ending time. So everyone is fine with this. If you have, even if you have a question, we'll have to reserve it for Thursday because we're already out of time. Okay. So that's it for today. And if you have any questions, please either email me or schedule an appointment for my office hour. So have a great day, everyone. It's a wonderful day. It's really a gorgeous day.
Thank you, Professor.
Have a good
All
day,
righty.
Professor.
All
Thank
right.
you.
Take care, everyone. All right. I will see you on Thursday. So stop recording.